Imagine walking through a sorghum field, taking a photo with your phone, and instantly getting an estimate of how many grains that plant is producing. No manual counting, no specialized equipment, just AI and a smartphone. And that's exactly what our research explores. Sorghum is one of the world's most important cereals, especially in dry regions of Africa, Asia, and the US. But improving sorghum yield is challenging because one of the key traits, the grain number per panicle, is extremely time-consuming to count. Breeders often rely on manual counting, which is slow, labor-intensive, and prone to human error. And in large breeding programs, thousands of plants need to be evaluated. This creates a bottleneck. We can't improve what we can't measure efficiently. And to support this task, we can leverage computer vision techniques, as has been successfully demonstrated in related fields. Computer vision enables computers to interpret and analyze visual information from images and videos. In particular, convolutional neural networks, the CNNs, can be employed to automatically extract meaningful features from images and also learn patterns that are relevant to the desired output. Furthermore, the widespread availability of smartphones equipped with high-resolution cameras and increasingly powerful processors makes them an ideal platform for deploying such solutions. By taking advantage of these capabilities, we can develop accessible and efficient systems that perform image-based analysis directly on our mobile devices. So in this study, our goals were to use the CNN architectures to first detect and segment sorghum panicles at the field using smartphone cameras. Second, using the images to count the number of grains. And third, estimate the number of grains of the whole panicle. No drones, no expensive cameras, no controlled environments, just real field conditions. And this is the general framework we follow. Don't worry, I'll break down as I'm presenting the steps. So let's start with the detection and segmentation. We collected 457 images of 20 different genotypes during the 2023 growing season in Kansas. These images were taken under natural field conditions, meaning variable lighting, wind movement, some occlusion, different panicle shapes and colors, and different backgrounds. This makes this dataset challenging for machine learned models, but also very diverse and realistic. Each image was manually annotated using masks. We augmented our dataset with auto-orientation, flipping, cropping, and adjustments into hue, saturation, and brightness. And we also resized the images to 640 by 640. In the end, we had around 4,500 images for training, 120 for validation, and 21 for testing. We set the training settings to 28 epochs, a learning rate of 0.001, and a batch size of 4. And we also used pre-trained weights. We input all this into two frameworks, Detectron 2 from Meta Research and the YOLO V8 from Ultralytics. In the end of our experiment, the YOLO V8 achieved the best performance, with an average precision of 89%. It also presented a lighter model file size and faster inference size, making it suitable for the mobile deployment. And in addition, in the same testing image, we can see that the Tectron 2 left some parts of the sorghum panicle behind. This can potentially lead to counting errors in our next step. And now, for the grain counting, we selected 40 random images from the previous dataset, and we cropped the full segmented panicle image into 3 equal patches, labeled the grains by placing dots where the grains were, and we reduced the size to 224 by 224. We augmented by changing the hue, the saturation, the value, the auto orientation, and flipping, generating 4,800 images. which were previously split into 80% training and 20% testing. The points were then converted to density maps using Gaussian filters. It kind of smashed the points, creating regions of different densities. But in the end, the integral of all the pixels in the images remains the same as before. We tested and evaluated three deep learning architectures used for crowd counting: the MCNN, which is the multi-column neural network by Zheng et al., TCNN seed, a model adapted for seed counting, for soy seed counting by Li et al., and we proposed a new architecture, which is Sorghum. The parameters were the same for all the three models: an L2 loss function, 300 maximum number of epochs with a patient of 20 epochs, a batch size of 8, and a learning rate of 0.001. The Sorghum, which is inspired by MCNN, and the other models tested in this study for the grain counting, use a multi-column feature extraction strategy. It extracts features in parallel using different convolutional layer dimensions and kernel sizes. This variable feature extraction strategy is important because the sorghum grains vary in size, density, and orientation. And in the end, the model predicts a density map, which is a heat map in which each pixel represents a probability that a grain or group of grains is present in that part of the image. When we look at the results, the Sorghum achieved the best performance in all the metrics we evaluated, with a mean absolute percentage error of less than 17%. Looking into the visual results, we can see that the Sorghum could identify the grains and generate the density maps with remarkable precision, very similar to the ground truth. And now, let's move to the whole-panicle estimation methods and the results. Before, we took a picture on one side of the panicle and we counted the grains in that size. Now, we need to estimate for the whole panicle. For that, 99 new panicles of the same 20 genotypes were selected, in addition to those used before. We're not using the same ones. Two images of opposite sides were taken. The panicle of in each image was segmented manually, and the grains were estimated using the trained Sorghum model. We then fit a linear model using the sum of the Sorghum output from the three patches and the manually counted grains from the panicle. We also compared the estimations from both sides to check if the side would present an impact when performing the estimations. When we compared both sides of the panicle, we obtained 103 grains of root mean square error and around 10% of error. Comparing the observed and predictions from the linear model, we obtained 17% mean average precision error, which is very low. And of course, our approach has some limitations. Lightning and shadows may affect accuracy, of course. Leaves and branches will occlude grains, affecting the precision of the counting, because we can count what you can see. Dataset size is still relatively small, mainly in genotypes, and smartphone cameras can vary in the quality, and panicles in the background, because we're in a field, can make the segmentation difficult, which can lead to potential problems in counting the number of grains in the image. But as future steps, we are working on several improvements. We are developing a multi-view imaging to capture the full panicle. We are getting more enlarged and more diverse data set across different environments, growth stages, and genotypes. We have almost real-time mobile app deployment, automated pipelines for breeders. This will help them a lot. And also combining grain count with other traits like panicle length and panicle width. which can be very useful for breeders. This approach has a huge potential for industry. Seed companies can evaluate hybrids faster. Breeding programs can phenotype thousands of plants with reduced labor. Agtech startups can build mobile tools for farmers. Crop insurance companies can use grain counts for risk assessment. And researchers can integrate this into yield prediction models, facilitating and accelerating their work. This is the end of today's video. I hope you learned something new. Don't forget to like the video, to subscribe, and to activate the notifications. Thank you very much.